Alrighty, this is the first in a hopefully ongoing series documenting the development of the Let's Space ARIES platform. So this is the Laterno University space program. Our long-term goal is to make a space shot, a rocket that will go over the Kármán line, which is, I believe, 100 kilometers up. And I'm the avionics lead this semester, and I'm working on this project. So what we're doing here, and this is just my understanding, the propulsion team knows a lot more about this, but how I understand it, we're developing our own rocket motors, solid rocket motors, and we want to be able to characterize them and get data from them, and obviously have a reliable, safe way to actually ignite them when we're doing testing. So we have all these systems. We have the actual motor igniters. Obviously, this is exactly the size of motors that we're using. Not really, but same idea. We're igniting rocket motors, and then we have sensors. So um, load cells, pressure transducers, potentially stuff like that. Where we want to collect data, and then we have a battery to power the igniters as well as the other systems. And then the remote controller, that's the ARIES. Oh yeah, ARIES, by the way, Advanced Remote Ignition and Evaluation System. I don't know if I mentioned that. The ARIES remote controller, or ARC, is going to be what you actually hold in your hand, and that's how you remotely control ARIES. And so ARIES is basically the black box that connects all these systems together, allows us to ignite motors remotely, collect data, and everything like that. So there's actually a lot of questions that need to be asked, and a lot of questions that I probably didn't ask when I should have. I probably should have asked a lot of these sooner. I kind of just went ahead and started making stuff, which was fine. I kind of learned a lot more about potential issues by doing that. But these are questions that I still really need to get the answers to, and hopefully we can do that at the start of this semester. But yeah, so what types of igniters will be used with the system? How much current do they draw? How long do they draw that current? Igniter might burn out in like 100 milliseconds. So even if it's pulling like 5 or 10 amps, that's different from like 5 or 10 amps continuously. How many ignition channels are we going to need? Do we need more than one? Are we going to want to test multiple igniters or multiple propellant grains at the same time without having to reset everything? So, do we need multiple ignition channels? What types of data will need to be collected? What types of sensors are we going to use? What rates and resolutions do we need? What specific voltages, like voltage values, do we need to measure? Is this like 3 volts, 5 volts? Are we in the millivolt resolution range? How's that all working? Also, another thing I thought of is ARIES actually going to be right next to the motor, or is it going to be some distance away? If we want it to be, when we're testing rocket motors, there's a potential for explosions. And so if rocket motor explodes, we don't want it to destroy ARIES, obviously, as well. I mean, ARIES is probably not going to cost more than $100, so it's not like a massive thing, but it would be nice to have a way to keep it safe. So maybe we put it some distance away, but then we have to transmit sensor data a really long distance. So how do we do that? Or otherwise, if we do keep it close, is there a way we can, uh, you know, sorry, I lost my train of thought. Is there a way we can, make it more explosion proof or durable in some way? And then also, for sensors, are we going to have like an analog digital converter, in ARIES itself to like permanently integrate, for example, a load cell? Or are we going to have, the ability to swap out different types of sensors, and what types of different requirements do those different sensors meet? So all that to say, a lot of different questions. Some of these I have some answers to, some of them I'm still trying to figure out. But yeah, that's just kind of an overview of things that we're trying to figure out with this project. Here's some big design goals. This was kind of what I wrote down initially. Sorry, I'm just grabbing my notebook real quick because I wrote some of this down in my notebook as well. Really, just the big goal is remote ignition motors for testing during propulsion development, as well as data collection from strain gauges and other sensors. And I just generally want it to be flexible and reliable, easy to replace parts, easy to upgrade, and stuff like that. So here's some other specific things, and I have kind of slides for each one of these. I'll just go through and, whoops, sorry, there we go. I'll just go through each of these and kind of talk a little bit more about why I made some of the choices I did, or or some of the factors to think about when making these design choices for each of these microcontroller radio through whole PCB, power architecture, MOSFETs, and the ADC. So, oh yeah, here's some other design choices as well. Um, Indicator LEDs on the PCB, jumpers for data buses, and some pin headers on the PCB as well. I'll talk about that more in a little bit. First, I'm just going to give you an overview of the PCB. So yeah, really the only thing I've done on this project so far is the PCB design. I have thought a little bit about the case design, the mechanical stuff. I haven't really done any work on that. That's the big main thing to do next. Um, but yeah, I just kind of started with the PCB. So we'll jump over to KiCad here. So it's still recording. Awesome. Okay, that's not the schematic. Okay, so this is the schematic I have at the moment. This is kind of, I actually haven't added a reversion, or sorry, a revision number yet, but this would be revision 0. I guess it's kind of, the base design. I'm probably, hopefully going to make a lot more changes before I actually order a PCB, but this is just kind of a place to start, kind of where I'm at now. So we have the Raspberry Pi Pico. That's the microcontroller I selected. I'll talk about that, why I selected that one a little bit more later. We've got the NRF24L01 radio here. That's going to be used to interface with the remote controller. This is the ADC I selected, the analog digital converter connected to the pyro circuits up here. That's actually a better way of selecting stuff. Yeah, so these are the pyro circuits. And then the ADC is also connected to this pin header here, so you can connect it to external sensors. We've got an SD card jack or socket, I guess. Over here, up here is the power circuitry. So we've got a battery. I'll talk about the power architecture more in just a minute. So we'll come back to all this. This is just to kind of give you an overview of what's happening. And then over here, we've got the pyro circuits for the igniter. So these jacks are what you would hook the igniter to. And then we've got the MOSFETs and voltage dividers, and I'll talk about that all more in a minute here as well. So yeah, voltage dividers, jumpers. Yeah, I can give you just a quick look at this. So the voltage dividers, actually, I probably should have pulled this up on my tablet first, but I can just show you here. So we've got a voltage divider circuit here. So what this is doing, basically all you need to worry about is this for now. So we've got the MOSFET, which is just acting as a switch. So that's an open circuit most of the time. So kind of block this out. Whoops, block that out. You've just got the battery going to the igniter and then going through these two resistors and then to ground. So that you have this current path just going through the igniter, through the two resistors, and through to ground. And so this allows us to measure the resistance of the igniter before we ignite it, so we can check for a good connection. And it does that by we have this voltage divider. So this way, the igniter is about 1 ohm, and then we have a total of 450 ohms of resistance here. And so the battery that's going to be powering this is 12 volts. And so I is U over R. So we're going to do 12 over 450, technically 451 with the igniter. That's going to give us about 26.6 milliamps. So it's going to flow a very small current through the igniter. And that's a small enough current that it's not going to go off. But we can measure the voltage right here, this pyro sense, which is going just into one of the ADC inputs. And then we also measure the battery, the voltage, using another voltage divider. The purpose of this voltage divider is just to get it down from 12 volts to less than 3 volts or less than 5 volts, so that it doesn't blow out the ADC. But we basically measure the voltage here, and then we do a bunch of math. With those two voltages, we can calculate the resistance of the igniter. I have done all the math for that on my tablet. I just don't have it on my computer to show you. But I have done the math for that. I should probably double check that. But yeah, that's how we're measuring the resistance of the igniter. And then, yeah, what was the other thing? Jumpers. So I have jumpers on the data buses for all the FPI chips. So everything is using SPI. Um, and we have the MOSI MISO, so master out, slave in, and master in, slave out. Those are the two data buses that are sending data between the Raspberry Pi and all three of these peripherals. And so I added jumpers on all of those because if I accidentally wired one of them incorrectly and just didn't catch it in the schematic, then I can, or the data sheet is like confusing and they actually need to be switched, then I can go switch those on the PCB a lot easier than trying to like do it, without jumpers there. So that'll make it a little bit easier to switch data buses if necessary. Just something I kind of saw online and seemed like a good idea for PCB design. So yeah, microcontroller, that's the first of those big design decisions I was talking about. So yeah, the microcontroller I selected is the, well, okay, so some options were the Raspberry Pi, Arduino, ESP32. Really, those are the only options I consider the popular ones. I selected the Raspberry Pi Pico because the main reason is it's used in Stella, which is our avionics for our avionics for our rockets. And those all use Raspberry Pi Picos. So I just wanted to stay consistent, and also I am transitioning from avionics sub lead to avionics main lead this semester, and so I'm trying to learn as much as possible about our avionics, and so hopefully this project will allow me to learn about the Pico system and programming the Raspberry Pi Pico, and then I'll be able to continue that on Stella's and have more skills in that area. Additionally, you can program Raspberry Pi Pico in either Python or C. It's very flexible, and it's also just cheap and really common. Everybody uses Raspberry Pis. There's a lot of resources out there. Super nice. So next up, the radio. The radio I selected, I really didn't consider this too much. This was just what Stella Avionics used. The previous revision, the most recent revision, actually uses a different radio, but these are just super popular. Everybody uses them, and they have a supposed range of up to 1,100 meters with the power amplifier and antenna. So, good range. Yeah, did not put a lot of thought into that. Yeah, okay, so next, through-hole PCB. So I decided to go with a through-hole PCB, no surface mount components for this revision. My thinking behind that was I can actually order through-hole parts, prototype everything on a breadboard first, have my entire PCB on a breadboard, get the code working or mostly working, and make sure that everything actually works, and then go ahead and order a PCB after that because I don't want to be, if I order surface mount parts, then I'm debugging, the PCB and my code and my schematic at the same time. All of those, I'm testing all of those at the same time. Whereas if I just prototype on a breadboard first, then I'm testing just the schematic and the components and the code first, and then I can get a PCB, and then I can troubleshoot the PCB. So it kind of it splits it up a little bit and should be a little bit easier to find problems along the way. Also, PCBs, well, through-hole components are easier to solder. I do want to learn surface mount soldering, but it's just going to be easier to do through-hole. That's a nice perk. And also, at least in the MOSFETs I was looking at, there's a higher current rating in general for through-hole components. Not that was not one of the reasons I chose to make a through-hole PCB, but kind of a nice side effect, I guess. Some of the cons, through-hole components are a lot larger, and it's also more difficult to route traces on a PCB with through-holes because every time you route a trace, you have to go around all the holes. You can't just go underneath the pads. So yeah, a little bit more difficult, but not a big problem. Okay, so let's talk about the power architecture. And yeah, I'm sorry, this is probably a really fragmented, unorganized presentation, but this is just kind of the current thoughts I had, mostly as a reference for myself. So the power architecture, we have three types of power in this PCB. There's 12 volts high current. That's coming from the battery. It's going to be like maybe a car battery or a motorcycle batteries, a large, probably lead acid 12-volt battery. That's going to power the igniters. That current also goes to the MOSFETs, so all the MOSFETs have to be rated for that current, which is probably going to be potentially, 5 to 10 amps, depending on the battery and stuff like that. But that's only for probably definitely less than a second, probably only a few hundred milliseconds max. Um, so yeah, it's high current, but for a very short amount of time. And then there's 3.3 volts. The Raspberry Pi runs on 3.3 volts, and all its logic is 3.3 volts, as well as the NRF radio and the SD card. Those are all 3.3 volts, and really everything could run on 3.3 volts. However, I decided to include 5 volts because I figured more sensors that we're going to use in the future, if we want to use a variety of different sensors with ARIES, we're going to want 5 volts just because probably more sensors are going to run on 5 volts than 3.3. The sensor header, pin header, does have a 3.3 volt and a 5 volt output, so we can use both of those. But 5 volts is just kind of more standard, I feel like. I probably should look actually at what specific sensors we're using to make sure there's a good motivation for 5 volts. But my thinking was just that it's more common, more popular, more things are going to run off 5 volts if we want to run more things, in the future. But yeah, 5 volts is additionally used to run the buzzer, which is on the PCB, and 5 volts is going to the input of the Raspberry Pi, which converts it to 3.3 volts. So let me show you that on the PCB. Again, I mentioned it earlier, but we have our battery coming in here. This is the 12-volt battery. That's going, it's coming in from the battery jack here, going to that battery sense, and then it's also going to all of the igniters here from that battery. And then over here we have a 9-volt battery, which is going to provide the 5-volt power. This is a 5-volt regulator, which is sending 5 volts here to the Raspberry Pi Pico through a diode. And then we also have 5 volts coming into the ADC here. And 5 volts is used, it's connected to the reference voltage through this pin header, which is acting as a jumper. So the idea behind that is you can have that jumper shorted to use 5 volts as the reference voltage. But if you want to use a different reference voltage, you can just take that jumper off, and then you can use whatever other reference voltage you want. So yeah, that's all the 5 volt stuff. And then 3.3 volts is coming out of the Raspberry Pi right here. Sorry, this is kind of confusing, but the 3.3 volt pin here is going up here, and then that's providing power to the SD card here, 3.3 volts, and also the radio chip. So yeah, all of those different voltage levels in the PCB. And yeah, so MOSFETs. So MOSFETs, what I found from the admittedly limited research I did is that igniters generally require 1 to 3 amps to fire. So all the power igniter circuitry needs to be able to handle at least that. However, if you have a 12-volt battery, and assuming the battery acts like a voltage source, which lead acid batteries are capable of providing huge amounts of current, there could be potentially, like 5 to 10 amps of current, a lot more current. So yeah, I tried to kind of build that into the PCB to allow for that current. The important things to think about for MOSFETs are the drain current rating. That's just the maximum current you can have flowing through, because you have basically, this is actually wrong. This should be 12. Oh gosh, no, that should be 12 volts. So you've got the 12 volts coming through the igniter, coming through the MOSFET, and then going to ground. This is just a simplified view of that circuit without all the voltage division stuff. And so you need to be able to have a drain current rating that can handle all the current that's flowing through the igniter. Next is the gate threshold voltage, which is the minimum voltage for the MOSFET to barely turn on. So you want a gate threshold voltage that is much lower than the voltage that you're actually driving it with. And the next is the drain source on resistance, which is the resistance between, across drain and source. when the MOSFET is turned on. You want that to be as low as possible. So the MOSFET I selected has these parameters: drain current rating of about 30 amps, which is more than plenty, gate threshold voltage of 2 volts max, and we're driving it with 3.3 volts. So that might be a little bit close, but it should be enough. And then we have drain source resistance of 14.5 milliohms at 4.5 volts. The data sheet is not very clear on this. It doesn't say what the drain source resistance would be at 3.3 volts. So I'm a little bit concerned about that. That's one of the main concerns I have with this MOSFET. But hopefully it's going to work. I'm going to order some and see if that actually do what I want. So yeah, next up, the ADC. So like I said, most sensors or more sensors probably will run on 5 volts than 3.3 volts. And kind of what I was thinking was speed is more important than resolution, because in rocket motors, everything happens very fast. And we want to be able to capture as much data while the motor's burning as possible, which only takes, like 5 seconds and or less, for smaller motors. And so we want to be able to capture as much data as possible, even if that means, at a little bit of a lower resolution. But I was able to, try to find something that is still high resolution. So we also need 8 channels, or the one I selected has 8 channels because we have 3 pyro voltage sensing inputs, 1 battery voltage sensing inputs, and then 4 sensor inputs, which could be 4 single-ended or 2 differential inputs. So it's configurable like that. And then the ADC I selected is 100 kilosamples per second max. So yeah, pretty fast. I mean, that's not like the fastest, but it's pretty fast. 12-bit. So that's the same as the Raspberry Pi ADC resolution. Pretty good. And then the reference voltage is configurable, like I was mentioning. The VREF pin is wired to this header, so you can short it to just wire it to 5 volts, or you can wire it to something else, using a voltage divider or something like that. Whatever sensor you need to connect. So next I'll go and show you the PCB layout itself. So this is the PCB layout I have currently. One of the big problems with this design is I waited to put the mounting holes until I kind of forgot mounting holes existed until I had everything routed, and so I went back and added those. But yeah, anyway, so you can kind of see the pyro circuitry on the right here with these really big traces. Those are designed to handle the current flowing from the battery through the MOSFETs. These are the MOSFETs here, 1, 2, 3, and then all the way back to ground. So yeah, basically we've got all the power stuff on, or the pyro stuff on this right side. We've got power coming in on the top here. So we've got battery, 9-volt battery, 5-volt regulator, LED for the 5-volt regulator. And then going over to the left, we've got the Pico here. I've wired all the unused GPIO pins to pin headers so that in case I want to use them for anything, I can without having to, do janky soldering on the PCB. And then moving down, we have the SD card here. I actually forgot to add an SD card until I had most of this PCB made. And then I realized that, oh yeah, we need somewhere to actually put data we collect. So I went ahead and added that. It actually fit really well in here. And then we've got the buzzer here with its MOSFET and resistors. We've got the radio down in the bottom left here. The antenna is going to stick out kind of down here. And then this is the ADC chip right in the middle here with the pin headers for all the sensors. And then, yeah, that's kind of the whole thing. We've got LEDs here that turn on with the pyro channels. So you'll be able to see those. That should help with debugging stuff. And yeah, so that's kind of the PCB layout. I guess, well, let's go to the next section because this kind of has to do with PCB. So some of the problems or concerns that I have with this current design, which I mean, really, I'm probably going to revise this quite a bit depending on design requirements. This was just something I wanted to have, a place to start, something to go off of, something that can, be changed. And I got a little bit of experience with actually designing PCBs, which was really fun. But yeah, so one of the big concerns, the components on the PCB are very close together. You can see here, there's only like I mean, what is this? Like less than a millimeter of space between those two components. So that's, really, really small. And some of the traces are kind of close together. I don't really know. I just don't have enough experience to know, what is an issue and what's not. But yeah, some potential concerns there. Yeah, like I said, I left mounting holes as an afterthought. Definitely will not be doing that again. I did manage to fit in four I think it was M2, yeah, M2 holes. So enough to be functional, but yeah, probably should have done that earlier. Um, yeah, MOSFET selection, like I said, I'm not sure if these MOSFETs are actually going to work with 3.3 volts. Another question I kind of had was about a ground plane for the PCB. Um, I did I kind of experimented with like making a big ground for like this, um, just like filling in all the unused space on the back layer with uh, a ground net. But I don't know if that's really necessary. I'm just not really sure. So um, yeah, that was another question I had. And then actually, let me. Well, yeah, okay. So another thing I had with the ADC selection, I found. Okay, so I found. Okay, so this is the ADC. Where's my? Okay, is it? Oh gosh, this is the ADC. Okay, so this is the ADC that I currently have selected. Um, this other ADC I was looking at, which this is a surface mount chip, but this is a TI chip. It looks really, really good. It actually specifically mentions, resistance temperature detectors, thermistors, and resistive bridge sensors, which is what load cells use. They have a Wheatstone bridge, and you have to measure very, very small changes in resistance. And so this is, basically designed for that. And one of the main reasons that it works is because it has a programmable gain amplifier built in, which is really nice. And the ADC I have selected now does not have that. I'm not sure if that's necessary. So I'll need to do a little bit more digging to figure out what we really need there. But that might result in a ADC change. This is a through-hole chip, or sorry, this is a surface mount chip. It's not through-hole. But I was considering potentially just getting a breakout board and soldering it on. You can get boards that will break out surface mount chips into through-hole chips, and so then you can put them in a breadboard and do work that way. So I might consider doing that, or just buy both and kind of see, what ends up working. But really, I need a better understanding of, uh, what our sensor requirements are first, I think. Yeah, next, just design rule check. I that's yeah, I haven't really done that much. I haven't. Well, I ran. Actually, I don't think I've run the DRC on my current version of the PCB. So definitely need to do that. Actually, make sure that I understand the requirements at JLC PCB. They have. This is where I'm planning on getting the PCB manufacturer. They have all these specifications here. So I need to go through and read those, make sure everything is actually up to spec. Um, yeah. Oh, I guess one more thing, real quick. I just want to show you the 3D model of this board. Maybe. Here we go. Okay. Yeah. So just another view. I wasn't able to find 3D models or the SD card or the radio yet, but yeah, kind of just a look at it. So we've got all our components. Pyro screw terminals here. Screw terminal for the battery, 9-volt battery jack. All the MOSFETs sticking up. And yeah, you can see the traces. If I fill that ground plane back in, you can see the ground plane on the bottom. This would also help with heat dissipation, so that could be good. But yeah, just another nice little look at that. So yeah, what is my last slide? Okay, yeah, further work. So obviously the remote controller, I have not hardly worked on that at all, besides just kind of throwing around some ideas of what I want it to be like. But yeah, gonna need to work on that. Also, this is not in this list, but I need to work on the case and the mechanical design for ARIES. I need to figure out what types of connectors and wires I want to use to connect to Pyro and to sensors and to batteries. So I need to work on that. I was also considering adding some LED warning lights. We have a little buzzer on the uh, PCB, but I think it might be nice to have some warning lights as well for when the system is armed to warn people. Um, and then, oh yeah, like I said, connectors for the sensor pins. Right now, I just have pin headers on there. Would definitely be good to have um, probably something else, JST connectors or um, I've thrown around some different ideas, maybe potentially even like RJ45 or VGA or something like that, to have a better connection than just pin headers. But yeah, so that's kind of where I'm at for that right now. Just wanted to kind of have this as an update, mostly just for myself, to have a record of the work that I've done. And yeah, I look forward to working on this more in the video. Thanks for watching and listening if you made it this far. Hope you have a good one.